The function sine of 1 over x has an interesting property. It oscillates just like a normal sine function, but as we will see, it oscillates faster and faster as x gets smaller. In fact, it oscillates infinitely many times in a finite space as x approaches 0. This means that the function has no limit as x approaches 0, even though the function is continuous close to 0. For this reason, we say it is a pathological function. This video is part of a series on calculus, and I also have a calculus book available. See the links in the description below. To understand the function sine of 1 over x, it is useful to first look at the normal sine of x function. This graph shows the function sine of x. The value of the function oscillates between +1 and -1. We can mark some special points on the curve. It has a value of 0 whenever x is a multiple of pi. For example, at pi, 2 pi, 3 pi, 4 pi, and so on, all the way to infinity. The function has a maximum or minimum whenever x is an odd multiple of pi over 2. For example, there is a maximum at pi over 2, 5 pi over 2, 9 pi over 2, etc. It has minima at 3 pi over 2, 7 pi over 2, and so on. What about the function sine of 1 over x? We can plot the same points for this curve. It has a 0 when 1 over x is pi, that is when x is 1 over pi. This corresponds to the first 0 on the sine x curve. It has another 0 at 1 over 2 pi, corresponding to the second 0 on the sine x curve, where x is 2 pi. Then again at 1 over 3 pi, and again at 1 over 4 pi. Notice that as the zeros on the sine curve move to the right, the equivalent zeros on the sine of 1 over x curve move to the left. That of course is because as x gets bigger, 1 over x gets smaller. Also notice that the zeros on the sine curve are equally spaced, but the zeros on the sine 1 over x curve get closer and closer together. This again is what you would expect, because the value of 1 over x increases more quickly as x gets smaller. Now we can draw the maxima and minima. The maxima occur at 2 over pi, 2 over 5 pi, 2 over 9 pi, and so on. The minima are at 2 over 3 pi, 2 over 7 pi, and so on. Now let's plot the curve. Since the special points get closer together as we approach 0, we can see that the sine oscillations get more and more compressed as we tend to 0. In fact, as we move towards 0, the cycles get so close together that we can't even see them on the graph. We can zoom in. This allows us to see the compressed part of the graph in more detail. But still, as we get closer to 0, the oscillations become too close to see. We can zoom in again. We can see even more of the graph, but again the oscillations are too close to see for very small x. In fact, we can zoom in as close as we wish. There will still be oscillations that we cannot see, very close to 0. That is because the curve oscillates infinitely many times before it gets to 0. No matter how far we zoom in on the curve, close to 0, there will still be more detail that we cannot see. We are going to look at the limit of this function next. As a reminder, here is the formal definition of a limit. For a function f of x, we say that the limit of f of x as x approaches a is L if for any epsilon greater than 0, there exists a delta greater than 0, such that modulus of f of x minus L is less than epsilon, whenever the modulus of x minus a is greater than 0 and less than delta. We can express this informally in a slightly simpler way. If f of x has a limit L as x approaches a, then it must be the case that when x is very close to a, f of x will be very close to L. If that statement is not true, then f of x does not have a limit as x approaches a. Here is the function sine 1 over x again. So far we've only shown the curve for x greater than 0. Since sine is an odd function, the curve of sine 1 over x for negative x is the same shape as the curve for positive x, but negated, that is flipped over the x-axis. Here is the complete curve. Notice that the curve is undefined when x is 0, because at that point 1 over x is infinite, and we can't find the sine of infinity. So we can't find the value of the function at 0, but can we find the limit as x approaches 0? Well, consider the region between minus delta and plus delta for some small positive value of delta. That region contains infinitely many oscillations, so within that region the value of the function will take every value between +1 and -1, and that will be true no matter how small we make delta. The condition for limit L to exist at 0 is that f of x must be close to L when x is close to 0. But we know that f of x will vary between +1 and -1 no matter how small we make delta, and for a very small value of delta, x will be close to 0. So no matter how close we get to 0, there will always be nearby points that have completely different values. So we can't say that all those points will be close to some limit value L. So sine of 1 over x does not have a limit as x approaches 0. This can be a bit hard to imagine, so here's a slightly different way to look at it. Think of the sine function as x gets larger and larger. The sine function will keep oscillating up and down forever. What is the limit of sine of x as x tends toward infinity? Of course there is no limit because the value of the function changes continuously. It never settles on any value. The same is true of the sine of 1 over x function as x approaches 0. But in that case the infinite number of oscillations is constrained to a finite range of x values. If you enjoyed this video, please like and subscribe. You can also join my Substack mailing list. This video is part of a series covering calculus. I also have a book to accompany these videos. The links are in the description below.